So in the previous lecture, we've started to set up this optimal control problem. We spoke about the properties, the kind of properties that a desirable vector field should satisfy when you are describing the dynamical system as x dot is equal to a function of t comma x comma u, right. We saw that with respect to certain arguments they have to be continuous, with respect to certain other arguments they need to be continuously differentiable. More importantly, one of the things that we pointed out was the fact that this vector field f need not be differentiable with respect to the input u, and also the input u needs to be only piecewise continuous in time. However, for much of what we shall set up today, we will assume that indeed f is differentiable with respect to u. The reason is this will allow us to approach this optimal control problem using the calculus of variations tools we have seen thus far. Okay, so this is before we launch into a formal proof of the maximum principle. Let us see that subject to making certain leeway, certain assumptions, how far we can push this calculus of variations tool to sort of at least get a glimpse of what the maximum principle ought to look like. Okay, so towards that end we just finished speaking about the vector field. Let's also talk about the kind of cost functional that we shall be dealing with mostly. So the nature of the cost functional would be something like this. Remember, we don't have x dot anymore, we have u in its stead. Okay, so that's the kind of cost functional that we are talking about. Of course, this will also depend on the system's initial conditions and initial states and so on and so forth. However, those are not in our hands. If you're given an initial condition at t naught, that's what you have to deal with. You cannot keep changing the initial condition to optimize your cost, right. The only choices you can make are through this u here. So this is the general form. Now this is the cost functional in the so-called Bolza form. There are two parts to this cost. One part which is known as the running cost. Okay, and the other part which is known as the terminal cost. Right. Now it turns out that through a suitable modification you can give this cost functional the appearance of something which does not have a running cost, and similarly you can also give it the appearance of something that does not have a terminal cost. The same cost functional can be appropriately modified so that it appears to have only one of these terms, and those are two special types of Bolza form. One of them is known as the Lagrange form, where the terminal cost is 0. The other is known as the Meyer form, where the running cost is 0. Let's see in general how you can go about it. Suppose you have this as your terminal cost. Now then, if we write this, what does this immediately suggest? The way I have written it, like the result of some integration, isn't it? What sort of an integration? Integration of what? Well, isn't it? Right? Now if we do this, What do we get? What follows as a result of this? Both of these arguments depend on time. So when you take a total derivative with respect to time, you have to take the partials and corresponding derivative of the argument with respect to time. So when you take the partial of k with respect to t and then the differentiation of t with respect to itself, that's just 1, right? So this turns out to be integration t naught to tf k. Let's denote that partial as a subscript. Fair enough? T xt dt plus, what about the next one? What about this? Partial of k with respect to x. So you can say that's like a grad, if x is a vector, partial of k with respect to x. Yeah, and then what do you do if it's a vector? Inner product, right? Component wise. So this is how we denote the inner product. What comes here as the next term? What is x dot after all? X dot is not u, that's only for the special case of a single integrator. In general, remember, x dot is required to satisfy this, isn't it? That's the dynamics. So we might just as well replace this here, right? This is the dynamical system after all. Let us not lose sight of this fact. So we might as well replace this with see, it's compatible, right? If there are n states, then f is an n tuple. This is also an n tuple, so it's an inner product. So what is the interesting observation here? This part was what was leading to the terminal cost. So now the terminal cost is just something of this form, which appears like a running cost. Yeah. So whatever was your original running cost, the one underlined in blue here, you just add this and this to this running cost, and the overall thing becomes your effective running cost. You might argue, well, hang on, what about this? So what about it? This is something, it doesn't matter, it's just a constant bias, isn't it? Given a T naught and an xt naught, it's just going to raise the value of the cost by a constant bias. T naught is fixed, xt naught is fixed. So wherever the function without this will have a maxima or a minima, the same is true of adding a constant bias to it. The location of the maxima and the minima doesn't change. The value of the cost functional changes, agreed. That's not what we are interested in. We are interested in the optimal control that minimizes. So the argument, the argmin is what we are interested in. The choice of u that makes it minimum doesn't change by adding a constant to the cost functional. So therefore, given a cost functional of this form in the Bolza form, if you wish to transform it to the Lagrange form, that is, give it the appearance of containing only the running cost and no terminal cost, then this is the technique you can adopt, right? So whatever was your terminal cost, you need to know its partials with respect to t and x. Of course, you assume that required degree of smoothness in k, that it can be differentiated with respect to x, it can be differentiated with respect to t. See, we are still trying to push our luck with calculus of variations, so we will require these additional smoothness conditions, and it is not a very unfair assumption, the fact that the terminal cost should be reasonably smooth in its arguments so as to allow us to differentiate. Okay, so you can go from the Bolza form to the Lagrange form. What if you wish to do the other way around, which is also interesting, in that you don't want any running cost, the same cost functional you represent in a manner so as to suggest that there is only a constant terminal cost at the end subject to where you have arrived at in the end. What do you do then? So then you have to eliminate this term. Well, that's quite easy. You see, you already have this. This is an n tuple, right? X is an n tuple. What if we did this? We designate the n plus first state. So let's say we just call it x hat, and we define that as, any suggestions? Okay, let's give the dynamics of that x hat dot. What do you think it should be? Our goal is to not have a running cost eventually. The same cost, by the way, will be represented in a manner such that it appears only as a terminal cost on my states and the terminal time. There is no running cost. So what if I designate this in the following manner? Sorry, I don't need this integration, that's bad. I just need the integration will come only when I. So this is the dynamics. So if I do this, if I define an additional state, so that now I have n plus 1 states. The original n states that are given, that are governed by this dynamical equation, dynamical system, this differential equation, I am just augmenting it. So now there are n plus 1 states. So this is like the first state, and the next states are of course f of t comma x comma u. And of course you will need an initial condition, so just set x of t naught is equal to 0. What do you think this running cost is going to now become? I had already written it somehow mistakenly. What is it? Now if you want to represent the total cost functional in terms of the n plus 1 states, what would it be? The running cost will just be taken care of by x hat tf, isn't it? Yeah, this will go ahead and replace this running cost, is it not? So this is known as the Meyer form representation. So once you are given a cost functional in the Bolza form, according to your wishes, according to how you feel convenient, you might wish to transform it either into the Meyer form, which comprises entirely of the terminal cost, or into the Lagrange form, which exclusively contains simply a running cost and no terminal cost, one way or the other, right? It's easy to go back and forth between these. Okay, all right. Is this part clear? So now we'll briefly touch upon the kind of target sets. Target set as in where we wish to land up finally, right? So practically speaking, if you want to park a car at a particular location, then your target set would be specified by the particular slot where you wish to place your car. And if you are very adamant about the time at which you want to park starting from now, then you will set yourself a final terminal time accordingly. On the other hand, you can give some leeway in either of those. So in general, when we talk about the target set, it is basically where we wish to eventually end up in. So this target set you could just think of as a subset of the following. Yeah, T naught is the instant when your mission is commencing. Yeah, so any time after T naught could be a potential final time. Yeah, until infinite. So you have the semi-open. This side is open, right side is open, and this is the entire Euclidean space from where your state space is drawn from. Yeah. So in general, your target set could be, for example, when you want to have a fixed time. I don't want to give you any time, you have to be exactly there at 1 minute 27.5 seconds. very precisely stated. In that case, this will become T1, but let's say I don't care where you go. So that's like a fixed terminal time. You could also have, for example, you could have the fixed terminal state. And you could specialize this to several different situations. For instance, one of the cases we had discussed earlier, if you remember, where we said that, well, the terminal state need not be fixed by a particular point, but rather it could be on a manifold. That's also a special case. You appreciate that, right? Because the manifold is just going to be contained inside your state space. Yes, so that's also a special case of this. So all of the cases that you can consider as your target set falls under this. Now, every once in a while we might need to be a little precise about what we mean by, suppose, this time that you have reached. So for example, there's a set in the Euclidean space that you have to reach. So what is the time? Suppose you go into that set and maybe out of that set and again go into the set and so on and so forth, or you go into the set and then live inside. So what is your terminal time then, if you have left it free? We will say then, the moment you enter the set for the first time, that is the smallest value of time at which you have reached your desired target set in terms of the state space part of it, that's what you will designate as the time of arrival at that set. And that's how long you should run your cost. The running part of the cost should run only till that instant. The first time you enter the desirable region in state space that you have set for yourself, if after that you leave or you stay within, so it must necessarily be the case then that this is a closed set, you understand? Because if it's an open set, you could just get arbitrarily close to it without really entering the set, and then it becomes difficult to define the terminal time. So we'll consider all of these cases as closed sets, closed subset of the state space, so that you exactly know when you've hit the boundary, that's the point where you have arrived at the set, and you'll usually say, okay, now I have arrived at the set, so this is the time till which my mission will run. Okay, so these are some of the specific cases. We will talk more about this when it becomes relevant later, but it's just good to be aware of the notion of this target set. Okay, sometimes we'll have fixed terminal time, sometimes we'll have fixed terminal state. What about the situation when we have this? The target set is entirely this. Do you think it makes sense? What I'm saying is, suppose my S, instead of being contained inside this, is exactly equal to this. What does it mean? Does it make sense? Does it? Seems like it doesn't make sense, no? Because you're already there. If the entirety, the moment you move ever so slightly away from T naught, you're already in the set. Even at T naught, you're already in the set because you're including T naught here in this interval and the entirety of the state space. So then, why should there be any motion? Is that right? Is it true to infer in such a situation that it doesn't make sense to have any motion and just to sit there, stay where you are at the initial position? You think so? Or is that a straightforward answer, right? You're already in the target set. Why should you budge? What do you think? The answer actually lies in the kind of cost function null that you have. It is not necessarily true, like George Orwell said, all animals are equal, but some are more equal than others. So all points in state space then seem equivalent, except that they are weighted differently by your cost function null. Just because you happen to be there in the target set at some point, it may not be the optimum location for you to be in. Yeah, you might be spending a lot of money because you're staying in Mumbai in a 1 BHK. Now, okay, staying anywhere in India is like your target set. You're in India. Does it mean you have optimized your monthly expenses? If you move to a say a tier 2 or a grade 2 or a grade 3 city with the same income, say you have a work from home job, with the same income, you'll be saving a lot more. So it makes financial sense then for you to migrate. Even though you are in India, you're already in the present, your goal is to ultimately settle down somewhere in India. But everywhere in India is not the same. Similarly, everywhere in this target set is not the same in terms of your cost functional. So even though it seems like you are in the target set, explicitly speaking, it appears like you are in the target set, implicitly, you would still want to move around within that target set until you arrive at a point which minimizes your monthly expenses, and in this case your cost functional. So it does make perfect sense to formulate a problem such that, in a crude manner, the target set is specified as equal to this. Even then, it is not a trivial problem to solve as to where you should go in the state space and at what time. So suppose you live in Mumbai, you also earn more. So you want to build up a certain corpus of wealth until you migrate to this tier 2 city. So how long should you live in Mumbai, and when do you make this decision to migrate from Mumbai? Yeah. So even though you're free to choose anything, and you might say, oh, I'm already there, why should I even do anything? Let me just sit there. That's not your best strategy, right? So just be mindful of that. Don't make sweeping assumptions based on how the target set is specified. Try to think about or account for the kind of cost functional that you have. Okay, so that is the important detail. Okay, clear so far? This is about the target set. So we've spoken about the vector field in the previous module. We've spoken about the two specific forms of the Bolzan form, that is the Lagrange form and the Meyer form, and now we've spoken about the kind of target set. So now we are sort of in a position to push forward with our calculus of variations based approach towards the optimal control problem. What has changed? The notation has of course changed. The fact that in original classical calculus of variations problem, you didn't have this u anywhere in your cost functional, you had effectively y prime x, which would have been replaced by x dot here, but now we are replacing it with u. So what do we need to be mindful of? That's what we are going to try and understand next. Any questions on whatever we've discussed so far? Is it all clear? Okay.